Good afternoon, everyone. Thank you for participating to today's ICCG webinar. Let me start saying that unfortunately the ICCG director Carlo Carraro could not be here today. So I'm introducing and moderating this webinar. I'm Marinella Davide and I'm researcher at ICCG. This is the second of a series of initiatives that the ICCG is organizing in the period of the UNFCCC COP23. Was negotiation just started yesterday in Bonn, in Germany. This webinar is particularly important because the presentation will be given by a researcher of the Woodsole Research Center, that is the winner of the ICCG Climate Think Tank Ranking Award. As you may know, the ICCG every year publishes a ranking of the top think tanks working on climate change. The ranking is compiled according to a series of indicators to assess the performance of hundreds of think tanks around the world. The Woodsole Center ranked first in our last 2016 edition, and if I'm not wrong, is the winner of this prize for the fourth year in a row. I'm therefore very honored to have Dr. Wayne Walker with us today. Dr. Walker is a scientist with expertise in forest measurement and monitoring, as well as remote sensing and RED+. These are also the topic of the webinar today. Before giving the floor to our speaker, let me briefly remind the rules. We have 30 minutes for the presentation and then a Q&A session. Participants can write questions through the GoToWebinar platform, and I will be in charge to read them at the end. So congratulations to the Woodsole Center, and thank you to our speaker for accepting our invitation. Wayne, the floor is yours.
Thank you, Marinella, for that very kind introduction, and thank you to the ICCG for giving me and the Woodsole Research Center this opportunity to highlight some of our recent research, and thank you all of you for joining here today. So as Marinella has said, I'm going to be talking about some recent research that we've published and highlighting that, but before I speak on that, I'd like to spend just a few more moments talking about the Woodsole Research Center itself. For those of you who may not know much about it, we're a small nonprofit research center located about 1.5 hours south of Boston in Massachusetts on Cape Cod in the United States. Our focus is to investigate the causes and effects of climate change, to identify and implement opportunities for conservation, restoration, and economic development around the world. We believe in the power of nature to slow climate change, and our work focuses on land-based carbon from the Arctic to the tropics. And I emphasize land-based because we're often confused with the Woodsole Oceanographic Institute, which is just down the road from our center. They're very well known. They focused on the marine environment, but we're independent from them. And as I said, our focus is on land and land-based carbon in particular. So with that, what I'm here to speak on today is recent research published just 3 weeks ago, October 13th, in the journal Science. The article was led by Alessandro Baccini, myself, and other scientists from the Woodsole Research Center and Boston University. It was titled, "Tropical Forests Are a Net Carbon Source Based on Above-Ground Measurements of Gain and Loss." And a little bit later on in the presentation, I'll be talking more about the specific results of this work, but I'd like to start out by what I'd like to describe as the status quo. So how were measurements of this sort done prior to this particular research, which we'd like to think is quite novel? So what was the status quo prior to this paper? Well, what you see on the screen right now is an intact tropical forest, although for our purposes it might not necessarily have to be intact. But for people like me who focus on the measurement and monitoring of forest across large areas of the planet, over the last decade or so, we've been quite good at estimating carbon emissions from forest loss. Okay, and when I'm talking about forest loss, I'm talking typically about deforestation, when all the trees are removed, and oftentimes there's a conversion in land use from forest to something else. For example, agriculture. Now, when we're talking about characterizing emissions from losses like this, what we need to know is we need to know the forested area, and we also need to have estimates of the carbon stock in the forest that was removed. And we typically get those estimates from forest inventory plots. So we end up with two knowns, if you will. The deforestation area is known, or the forest area of forest loss is known, and in the parlance of the IPCC, that's known as activity data. The other known, of course, is the average carbon density, and that is typically referred to as the emission factor. When we put those two together, we can plug them into this equation, which gives us gross carbon emissions. Now, what I've just described really only applies to the left-hand portion and this deforestation component of this equation. What's important to recognize is that for the most part to date, the right-hand portion, this degradation portion of the equation, has been largely ignored. And it's been largely ignored because when we're talking about estimates of area loss, they don't, strictly speaking, apply to degradation. So this has become quite a challenge and something that we specifically wanted to try to address in our own work. So just so that we're all on the same page about some of these terms, on the left-hand side you have intact forest. In the middle panel you have degradation, and for our purposes degradation here is being described as a region where forest is remaining forest, however there's been a loss in carbon density. All right, so trees have been removed, but the land use has not changed. If you were to walk into a degraded region of forest, you would still consider it to be a forest. It would look like a forest, however degraded. Some of the trees have been removed, but for the most part, forest function on some level still remains. In the right-hand panel, of course, you have deforestation, where virtually all the trees have been gone. And again, here we're talking about a conversion to an alternative land use like soy agriculture, which is the case in the picture on the far right. So, as part of the status quo, we at the Woods Hole Research Center have been contributors. And the way in which we've contributed to date is by producing snapshots of above-ground carbon density. What you see at the top of the screen is one of those snapshots. It's a snapshot from the 2007-2008 time frame. It represents above-ground carbon density for the pan-tropical belt at a resolution of 500 meters. This was published by Bacchini et al. In 2012 in Nature Climate Change, and at the time it was unprecedented in terms of the resolution. When I'm talking about resolution, I'm referring to the fact that if we carve up the pantropics into a grid, wherein each grid cell represents 500 meters by 500 meters, what you have in this map is an estimate of carbon density from the forest in each one of those cells. Okay? Now, more recently, we've worked to increase the resolution of these snapshots. We've gone from 500 meters on the left to 30 meters on the right, and you can see the difference in the amount of detail present in these maps. This 30-meter map is produced for the globe for the year 2000. So what we did recently was we took that year 2000 map of above-ground carbon density and we combined it with global forest cover loss data from Hansen et al., which was published in Science in 2013, for the period 2000 to 2015. Okay, so at the top we essentially have our emission factor data. At the bottom we have our activity data. We combine the two. We essentially use the bottom map to eat through the values of the top map. And what we end up with are estimates of annual gross emissions from forest cover loss. So in this animation, you see time changing in the upper left from 2000 to 2012. The animation itself shows deforestation area increasing in orange. And just beneath, back in the upper left, just beneath the year, you see the amount of carbon being lost since 2000, since the beginning of the time series. So what you have, excuse me, what you have here are these annual emissions, again from forest cover loss, okay? And with data like this, we can present information of the sort you see on the screen here. This is work published in 2015 by Zarin et al., representing annual gross emissions from deforestation. What you have here are 16 countries, and in each plot what you have is the trajectory of gross emissions from forest cover loss. And you can see each country has its own story, if you will, of gross emissions. If we look down on the lower right, you'll see Costa Rica, for example, which of course has a long history of forest conservation and conservation overall. And you can see the trajectory of emissions over time are quite flat, as we would expect. Now, if you go up to the upper right, where you see the Democratic Republic of the Congo, you can see quite a different story, with emissions increasing quite rapidly, particularly in the more recent post-2010 timeframe. Okay, so very different pictures of emissions over time based on sort of the status quo approach. So what are the limitations of the status quo? Well, as I've already suggested, gross biomass losses are estimated from deforest only. Okay, in the case of deforestation, the damage to the forest has already been done. However, where degradation is concerned, which of course hasn't been captured in these existing approaches, hope actually remains, because again, the forest is still present. Okay, it's degraded, but again, in terms of function, there's still some of that remaining. And so degradation to us represents a really important place in which intervention needs to happen. Because once deforestation has occurred, a change in land use has happened, there's only then so much that can be done from a restoration standpoint. It takes a lot more effort to put that forest back. However, in the case of degradation, the forest is still there, the land has not been converted, and as I said, hope remains. Now, additionally, one of the limitations, of course, is that this status quo approach is unable to address gains in biomass from growth or from uptake. These gains tend to be ignored, but of course, where the climate's concerned and climate mitigation is concerned, they're very important. So what I'd like to talk about now is what we'd like to think of as a new paradigm, moving from the status quo into what has been the basis for a recent publication. So how do we go about doing this? Well, let's go back to our snapshot from 2007, 500 meters. If we zoom into an area of Brazil, you see sort of the typical fishbone pattern here. We're just looking at carbon density, wherein the dark green values now are areas of high carbon density. Darker red values are regions of much lower carbon density. Okay, think deforestation. So that's all well and good, but ultimately what we'd really like to have are maps through time that tell us directly about the changes that are happening. You can imagine going back in time. You can imagine going forward in time. You can imagine having an annual map that consistently and accurately provides estimates of the carbon density. When you put these together, you can estimate changes. So what you see on the left now is essentially the result of this sort of approach. Each plot that you see here, of which there are 3, each plot is one 500 by 500 meter pixel. The x-axis is time from 2003 through 2014, a 12-year period, and it's labeled as 1 through 12. What you see on the y-axis is biomass, and what you see in the plot itself is the trajectory of change. The black dots represent the values from the 12 maps at the pixel level. The blue line represents the fitted value, which is the result of a change point algorithm that we developed for the purposes of this work. So what you see in the top pixel is a small decline in biomass in the first year, followed by a gradual increase over time through the end of 2014. In the middle, you see a slight increase, followed by a precipitous drop, and then some variability declining after that. And finally, at the bottom, you see what we consider to be a stable pixel. There's quite a bit more noise here in the estimates, but statistically speaking, we consider this pixel to be unchanged. Now, if we look at this now in map form over a much larger area, many more pixels, specifically 190 kilometers by 215 kilometers, what we see is the mapped manifestation now of this work. In reds, we see losses. In greens, we see gains. In yellow, we see stable. So now what we're able to provide here are estimates of change, not only showing where the change is happening, but also the amount, the magnitude of change that's occurring. Now, if we compare this map with the work of Matt Hansen, again, Matt produced estimates of forest cover loss. He published this in 2013. If we overlay those estimates in black, we see a relationship between the darkest red pixels and the Hansen data in black. Now, the darkest red pixels, of course, is where the biomass losses, the carbon density losses are the greatest, and where we would expect, therefore, to see losses in forests due to, among other things, deforestation. Okay, and we see a very good relationship between those two. Oops. Now, what I'd like you to notice as well, however, is if we look at the regions around the forest loss area shown in black, you see areas of lighter reds and pinks. Okay, these are areas where we see degradation, lower amounts of loss, not full-blown deforestation, but rather degradation. So here we're capturing losses from both of these different processes. So as I mentioned at the beginning, we published this work recently in Science. This is the map that was the principal figure, figure 1 in the paper. It's pantropical and represents above ground carbon density change for this 2003 to 2014 time frame. Again, greens are gains, reds are losses. So what were the main results of the work? Well, as the title suggests, the region as a whole is a net source of carbon to the atmosphere. I've had people recently ask me if that means the forests are no longer doing their job. That is, of course, not exactly correct. What is happening is that we are no longer doing our job in terms of forest protection. What this means is that forests in the region are being lost at a rate faster than the remaining forests are able to take up the carbon. So what you see is a net loss of 425 teragrams per year. You can see in the middle the distribution of those emissions across the continents, with, not surprisingly, the most coming from the Americas. What's also interesting about this work is that we found that at the scale of the pantropics, roughly 70%, 68.9 to be specific, percent of those total losses came from what we're calling degradation. Okay, these losses that were not previously accounted for in what I described as the status quo. So just to review the strengths of this new approach. Well, as I've mentioned, here we're able to account for losses in forest carbon from not only deforestation, which of course has been done, but also from anthropogenic disturbance, otherwise known as forest degradation, as well as natural disturbance. Here we're talking about wind throw, we're talking about fire, we're talking about drought, we're talking about insects and diseases. Now, in our work, as the map currently stands, you cannot, strictly speaking, separate natural disturbances from anthropogenic disturbances. However, we're now working with ancillary data sets and collaborators to separate as best we can the anthropogenic drivers from the natural drivers. So that's ongoing work. Of course, as I already said, we're now able to account for gains in forest carbon from growth. And so when we put these losses together with these gains, what we're able to provide is essentially an estimate of what the atmosphere is actually seeing, which is something that hasn't been done before. And finally, what we're able to do as a whole then is track changes that we see in forest carbon with greater frequency, consistency, and accuracy than was previously possible. So where are we going from here with this work? Well, first of all, we're very eager to expand the research from the tropics to the globe. We want to be able to produce what is a more comprehensive picture at the planetary scale, and we're very close to being able to do that. I hope within the next 6 months or so you should be seeing global work. We want to better automate the process. As you saw, the current research ends in 2014. We want to be able to update this annually, and we're nearly capable of being able to do that now. But not just annually, potentially even sub-annually. So think quarterly, think perhaps even monthly. And finally, we want to increase the spatial resolution of this work from 500 meters to 30 meters. I talked earlier about how we're able to do that with these singular snapshots of above ground carbon density, but we'd like to be able to do that with the change process. And just to give you a sense for what that would look like, this is now using a Landsat data, which provides us with what is a much longer time series than the MODIS aqua and terra sensors that we're using currently. And both of these data sets are provided by NASA, freely available data. But with MODIS, we can only go back to the early 2000s, where with Landsat, we can go back much further. This is what you see on the screen here are 30-year trajectories, the same pixel level sort of trajectories that you saw previously at 500 meters. Here's 2 of them now at 30 meters, 30-year trajectories instead of 12. And with such a long time series, now you get a much, much better sense for the change, as well as the drivers of change, because with these trajectories, you're able to potentially assign signatures of change that are only associated with particular types of change, and potentially allow one to actually assign a driver to the trajectory based on a classification of the signatures that you see. So we're quite excited about this. And with that, I appreciate very much your time this afternoon, and I thank you. And I'd like to open up the floor to any questions that you might have. Thank you so much.
Sorry, thank you very much, Wayne. Really interesting presentation, and I had the opportunity also to look at the paper. Very well done study. I will allow for more time to receive questions. I will break the ice asking a question myself. Working on climate governance, one of the things that I first thought when after reading your paper was, and so what we should do now. So actually your approach and your findings are, let's say, changing the perspective of forestry that is usually considered as a carbon sink. So this changes both so my question is, what are the policy implications of your findings? I'm thinking to both to REDD+, to the REDD+ framework. So we should prioritize different mitigation action, as we know that forests are also can be a net source. And I'm also thinking to the reporting of emissions by countries like Brazil, Indonesia, that I don't know, I'm not an expert, they maybe should change the way they are accounting for land use change emissions. Can you say something on this?
Sure. Thank you, Marinella. So a couple of things. First of all, while I appreciate your point about this change in perspective, I think it's important to emphasize that forests themselves remain a sink. It's the region that is a source. That is to say that where the forests are present, okay, where they are healthy and functioning, they remain, as they should, a sink. It's obviously when they're being lost, that then shifts the balance towards a source. So while, yes, this is concerning when we see this comprehensive picture of what's going on the ground, it also represents quite an opportunity, I think, from a policy standpoint, because obviously in the context of the Paris Agreement, the NDCs, each country's individual efforts, each country's individual commitments to reducing emissions under the Paris Agreement, clearly forests represent an opportunity that perhaps they weren't representing before. While the story has changed somewhat, forests, where climate change mitigation are concerned, are still what I would describe as the lowest hanging fruit in terms of mitigation. That is to say, there is no less expensive, easier to implement strategy for carbon sequestration than forests. I mean, of all the engineering solutions that have been put forth, forests obviously are still the best. Now, they can't be the only answer, and they shouldn't be the only answer to the problem of climate change. Obviously, we need to address fossil fuels and so forth, but in the short term, more can clearly be done to not only address deforestation, which obviously a lot of work has already been done on that, but also to address the degradation issue, which I think has flown beneath the radar a bit insofar as it's been harder to detect, harder to measure, and hence somewhat forgotten about. But now that we have maps and we can see where this is happening, there's an opportunity to use them to intervene. So I think the story is that of course there's more work to be done, but now we know better where to focus our efforts in the context of the NDCs, in the context of associated policy making.
Thank you very much. Yeah, it's an interesting debate. Let's start with the questions from our audience. Okay. We have a question from Francesca. As a non-expert of the topic, have you thought? She has a curiosity. Have you thought about an economic evaluation of losses coming from forest degradation to see how they differ from forest deforestation? Would that be possible using the new paradigm?
I think it would absolutely be possible, and I think it represents work that certainly needs to be done. I've spoke recently, since the paper came out, to a few economists who are very interested in this topic. Obviously, I'm not an economist myself, but clearly there's data to be extracted from our results that could feed into an economic analysis, and I think that's certainly ripe in terms of the next research steps.
Okay, thank you. And another question. you account for above ground carbon density, accounting also for below ground density. Would this change the balance? And also, actually, I have two questions. And also, do you expect the same results from broadening the coverage of your analysis, so extending the analysis beyond tropical forests?
Right, right. So I'll take the first part. You're correct. This research focuses above ground. We're starting to look below ground. A colleague of mine at the Woods Hole Research Center, Jonathan Sanderman, is a soil scientist, and he is looking at the below ground component. Has recently published some work on the topic in PNAS, and we're looking at the extent to which we can bring together above ground and below ground. I think the extent to which the below ground results would impact what we already see in terms of the above ground results, I think it would vary a great deal, of course, by region and even by country. Obviously, in places like Indonesia, where above ground forest loss has been accompanied by below ground losses of peat and the carbon associated with it, you will only see a greater loss, okay? Whereas in other regions, while the forest above has been lost, the below ground portion, while it may be declining, is declining certainly at a lesser rate than you would see in peat, associated with peat fires, for example. The story, however, is probably that if you on the whole, if you include the below ground portion, the losses are only at the scale of the region, the losses are only increasing as opposed to decreasing in terms of net emissions. Now, when we expand the work to the globe, in many parts of the northern hemisphere, you're seeing increases. You're seeing, you see countries like the United States where there's probably more forest now than there has been since pre-settlement times, for example. In the boreal zone, as a result of climate change, actually, you're starting to see greening. You're starting to see the encroachment of shrub cover in places that you didn't see it before. So in many places you're gaining more than you're losing. Of course, again, it's variable. That's not the case everywhere. So quite frankly, it's going to be interesting to see at the scale of the globe what the net balance is. I'm not sure at this point that I'm confident one way or the other.
Yeah, it's a tough question to answer. I will go ahead. We have a couple of further questions. Can you say a bit more about the drivers of disturbance? You mentioned the natural disturbance, but what are the drivers of man-made of anthropogenic disturbance, and can they be related to better forest management practices?
Well, certainly improved forest management practices, low impact extractive processes could certainly are certainly worth implementing and could have a real positive impact. But that's obviously limited to sort of one sector for the most part. If we think of it in the context of the timber industry, beyond that, of course, we have we have any number of drivers. You have the transportation sector. You have the hydroelectric sector. You've got agriculture. You've got petroleum, mining. All of these different sectors and the forest loss that goes along with them are driving what we're seeing here to a greater or lesser extent, depending on exactly where you are. And each one of those drivers requires its own sort of suite of interventions to lessen the blow, if you will. So it's obviously, as we know, a complex problem to deal with. There is no silver bullet.
Thank you. And I have another question. Looking ahead, what's one question that you are most excited to explore next using this novel approach?
Well, actually, one of the most exciting questions that is not directly related to this work, but is sort of a takeoff from it, is looking at potential above ground carbon storage. So you can imagine we're able to map reasonably accurately carbon stocks at one time. We've been able to do that for some time now. Now we're able to map changes over time. But what if we could map the potential for landscape restoration, for carbon to be put back on the landscape? So if we take a map of carbon stocks and we remove the influence of humans, anthropogenic influences, and we estimate what the carbon would be in the absence of everything that we've done to the planet where forests are concerned, and you subtract one from the other, it gives you the unrealized potential of the landscape to store carbon. And with this map of unrealized potential, which is something that we're working on right now and hope to publish early next year, you have now a theoretical map of how land management can be optimized. Not just for economic gain and all the other sorts of important things that we need to recognize, but also doing so in a climate smart fashion. So how do you get the biggest bang for your buck in terms of climate while also feeding the planet, while also developing one's economy, etc. And with the data that I've shown today, if you make interventions based on such an unrealized estimate of restoration in terms of carbon, with the data that I presented today, now you have a tool for tracking performance against interventions, against goals on the ground. So all these pieces sort of fit together. That's sort of what I'm most excited about.
Thank you. I think we have no further question. A final question about the last minute question about the blue carbon. Do you think that the same approach can change the results also about the potential of blue carbon sinks?
Well, I'm certainly not an expert on blue carbon. And as I mentioned at the beginning, our work at the Woods Hole Research Center focuses, almost exclusively on land carbon. Obviously, we can't just look at any one of these areas in a vacuum. We can't only look at forests. We can't only look at blue carbon. We have to bring these pieces together. We have to look at them collectively if we want to have the proper picture that we need to have of the carbon cycle and what it means for climate change moving forward. So while I'm not an expert on blue carbon, obviously the results I presented today have implications for that, and the work of scientists on blue carbon obviously have implications for what we're doing here in sort of the global sense.
Yeah. Thank you very much. I think that we are going toward the end of this webinar. We look forward to see your future findings, the extension of this work also to the rest of the world, and yeah, thank you very much, Wayne, for being with us today. Very interesting presentation, and thank you all the participants. See you at the next ICCG webinar that I think is tomorrow with the best climate practice webinar. Thank you very much. Hello, bye everyone.